Hello everyone, I'm Jiang, and I'm glad to talk about our recent work, Efficient Hyperparameter Optimization with Adaptive Fidelity Identification. The performance of machine learning models strongly depends on hyperparameters. This work focuses on hyperparameter optimization, which is a research topic that aims to automatically find hyperparameters that achieve suitable performance. One type of method is model-based method, and most of them follow the Bayesian optimization framework. It begins with evaluating some random configurations to get the performance. The results are added to the observed data points, which are used to update a surrogate model. Then the acquisition function is used to identify a permitting configuration to be evaluated. The process repeats, and we can finally get the optimal configuration. The biggest limitation is the expensive full evaluation for the configurations. Multi-fidelity methods consider performance at different fidelities. They follow the successive halving framework, which evaluates many configurations using limited resources and iteratively promotes the better performing half to continue evaluating using double resources. However, multi-fidelity methods randomly select configurations, so they can't use historical evaluation information to guide the selection. Recent research combines these two types of methods to take advantage of both. They follow the SHA framework and replace random sampling with BO. However, learning curves of different configurations can intersect, so the early performance they got through some fixed fidelities can't always indicate the final fidelity performance. As shown in this example, if we use this low fidelity performance to feed the surrogate model, it will reflect inaccurate information. So this leads to a fundamental challenge. What is the appropriate fidelity for each configuration to feed the surrogate model? To answer this question, we first introduce a concept of efficient point of each configuration. Intuitively, it means that starting from this point, when the resources are doubled, the performance improvement falls below a small sharehold. So it is a fidelity that can get strong performance while still efficiently using resources. We use this point as the fidelity to feed the surrogate model. To further save resource usage, we introduce another concept of saturation point. It means that beyond this point, the performance does not have notable variations with more resources. So we use saturation point as the approximation of the final fidelity. Both 2 points can be adaptively obtained for each configuration from its learning curve. With the 2 crucial points, now I briefly introduce the process of FastBO. Every configuration first experiences a warm-up stage. The configuration is evaluated to a predefined point and get its early observation set. Then we estimate its learning curve from its observation set. After that, the 2 crucial points can be adaptively extracted for every configuration. Then the configuration continues to be evaluated to its efficient point and use the result to fit the surrogate model. Finally, the post-processing stage lets a small set of best-performing configurations resume evaluating to the saturation point and find the optimal configuration. Here we highlight the generality of FastBO. The idea of FastBO provides a simple way to extend any single fidelity method to multi-fidelity setting, which is evaluating the configurations to their efficient points. We also show in the experiments that this strategy is effective. Particularly, REA is not a model-based method, and it also can be extended using our strategy to improve its efficiency. Our experiments were conducted among 11 baseline methods, and we showed that FastBO can handle various performance metrics and show strong anytime performance. It gains an advantage earlier than other methods. And results also show that FastBO saves 10 to 87% time when achieving better performance values. We also conducted experiments to show the effectiveness of the adaptive fidelity identification strategy. So in conclusion, first, We propose a multi-fidelity model-based HPO method that adaptively decides the fidelities for configurations, thanks to the introduced concepts of efficient and saturation point. Second, we develop a learning curve modeling module to adaptively extract the key points, a warm-up stage for early termination detection, and a post-processing stage for efficient evaluation. Third, our strategy can be used to extend any single fidelity method to multi-fidelity setting.